Hello, welcome to another module in this massive open online course. So, we are looking at the Z transform and its properties. So, let us continue our discussion on this very important transform for discrete time signals and systems termed the Z transform. Remember, we have already seen the definition of the Z transform. X of Z equals summation n equals minus infinity to infinity x of n z raised to minus n, and the ROC, the region of convergence of the Z transform, is the values of Z for which this converges, for which this possibly infinite summation converges. Okay. Now, let us look at the Z transform. We are looking at the Z transforms of some common signals. We have looked at the Z transform of the unit impulse and the unit step function. Let us look at the Z transform of a cosine signal, that is cosine omega naught n u n, which, as you know, cosine omega naught n can be written as, so this is basically cosine omega naught n can be written as half e raised to j omega naught n, half e raised to j omega naught n plus e raised to minus j omega naught n times un, and the Z transform of this is x of z, which is half summation n equal to minus infinity to 9 infinity e raised to j omega naught n plus e raised to minus j omega naught n un z power minus n. Now, un is non-zero only for n greater than equal to 0. So, this is equal to half summation n equal to 0, n equal to 0 to infinity e raised to j omega naught n z power minus n. So, this is e raised to j omega naught z inverse raised to the power of n plus half summation n equal to minus infinity equal to 0 to infinity e raised to minus j omega naught z inverse raised to the power of n, which is equal to, well, this is 1 over, or this is half, the factor of half is there, 1 over 1 minus e raised to j omega naught z inverse plus half 1 over 1 minus e raised to minus j omega naught z inverse, e raised to minus j omega naught z inverse, correct. And if you sum this, this is equal to half. In the numerator, you have 1 minus e raised to j omega naught z inverse plus 1 minus e raised to minus j omega naught z inverse. So, 1 plus 1 is 2 minus e raised to j omega naught plus e raised to minus j omega naught is 2 cosine omega naught z inverse divided by 1 minus e raised to j omega naught z inverse into 1 minus e raised to minus j omega naught z inverse is 1 minus 2 cosine omega naught z inverse plus e raised to j omega naught into e raised to minus j omega naught is 1 z minus 2, okay, and this is equal to, well, 1 minus cosine omega naught z inverse by 1 minus 2 cosine omega naught z inverse plus z minus 2, which simplify by multiplying the numerator and denominator by z raised to minus z square. So, that will give you z square minus cosine omega naught z, or minus, I am sorry, there is a factor of 2 over here, or there is a factor of, there is no factor of 2. So, this is z square minus cosine omega naught z minus cosine omega naught z divided by z square minus 2 cosine omega naught z plus 1. And the region of convergence, remember, this has two poles, that is e raised to j omega naught and e raised to minus j omega naught. So, the two poles are, there are two poles, P1 equals e raised to j omega naught and P2 equals e raised to minus j e raised to minus j omega naught, and therefore, the ROC, remember, ROC equals magnitude of z greater than magnitude of e raised to j omega naught, comma, it has to be greater than magnitude of both poles, and magnitude of both poles equals 1. So, ROC is magnitude z greater than 1. This is the ROC and this is the z transform of cosine. This is the z transform of cosine omega naught n times u of n. Okay, so, this is the z transform of the signal, all right, and the ROC is magnitude of z greater than 1, all right. And now what we want to do, so we have looked at the z transform of some of the common signals such as the unit impulse function, the unit step function, cosine omega naught n, where omega naught is the frequency times un, all right, and you can derive the z transform of some other common signals, for instance, such as sine omega naught n into u of n, un, and so on, etc. All right. What we will do now is look at some of the properties, the important properties of the z transform. So, what we want to look at next is the properties of the z transform. Properties of the z transform. Now, the first property is the z transform is termed the linearity, that is, the z transform is a linear transform, which means to say that basically if I have x1 n, and this is similar to the Laplace transform, x1 n has z transform x1 z and ROC is R1, x2 n has z transform x2 z, ROC is R2, then this implies that A1 x1 n x2 n will have z transform A1 x1 z plus A2 x2 z, that is a linear combination, that is A1 times x1 n plus A2 times x2 n, there is a linear combination of the input signals results in a linear combination of their z transforms, the same linear combination, that is A1 x1 z plus A2 x2 z, all right. This is the linearity property, and the ROC will at least be greater than the intersection of the two ROCs. So, the ROC will be a superset, okay. or you can simply say, let us say the ROC is basically the intersection of R1 intersection R2. It will at least be this in practice, it can be, it is a superset, alright. So, it can be more than R1 intersection R2. Okay. Let us look at another property. The time shifting property, that is, let us say x of n has the z transform x of z, okay. Then your x of n minus n naught, what is the z transform of x of n minus n naught? Now, you can see, let us consider this as x tilde n with z transform x tilde z, then x tilde z equals summation n equals minus infinity to infinity x tilde n z to the z raised to minus n, which is n equals minus infinity to infinity x of n minus n naught z raised to minus n. Now, set m equals n minus, now this implies n equals m plus n naught, and the limits will still be infinity minus n naught, which is minus infinity, to infinity minus n naught, which is infinity. X of n minus n naught is x of n, z raised to minus n is m plus n naught, which is equal to, now if you take the z raised to minus n naught outside, z raised to minus n naught, this is m equal to minus infinity to infinity x of m z raised to minus m, and remember this is x of z. So, this is x tilde of z equals x of z into z raised to minus n naught, alright. Or basically to say your delay x of n minus n naught, signal delayed by n naught, has z transform z raised to minus n naught x of z raised to minus n naught x of z. So, this is a delayed signal this is a signal delayed by n naught, and this is the z transform of the signal, that is its original z transform multiplied by z raised to minus n naught. Now, this for the special case where n naught equal to 1, that is for a unit delay, this will simply become z inverse, that is z raised to minus 1 times x of z. Therefore, this operator z inverse, that is z raised to minus 1, is also termed as the unit delay operator. Frequently you will see it using to represented used to represent the structure, alright, used to represent a filter, correct, in which a signal or a signal sample xn is delayed by a unit delay. To derive xn minus 1 is represented using the operator z inverse, or using the block z inverse, which represents a unit delay, or a unit sample delay. So, for n equal to, for the special case of n not equal to 1, that is a unit delay, we have x of n minus 1 has the z transform z raised to minus 1 x of z. So, this is also termed as the unit, this is also termed as the unit delay operator, and frequently you will see this in systems, when you represent a system, typically you have a block which looks like this, which means you have a block which means if the input is xn, then the output is xn minus 1. So, this is simply a delay block or unit delay block. Okay, so this is a delay block that is used to represent a delay, a sample delay, and you can consider construct or you can link several such blocks to basically delay the signal by an arbitrary amount. For instance, if you connect two such blocks in series, the net signal will be delayed by 2 times. So, xn minus 1 and the output will be xn minus 2. Okay, and then you can do processing on xn minus 1, xn minus 2 and so on. Okay, all right. So, let us go on to the next aspect, that is basically your time reversal. Okay, so let us look at the time reversal. In time reversal, what we have is x tilde n equals x of minus l, and let us say the ROC of the Z transform is R. So, you are basically reversing the time. For instance, if xn is not, that is basically you are reflecting it about the y axis. For instance, if xn is 0 for n less than 0, then this x tilde of n, which is the time reflected, time reversed version of xn, will be 0 for n greater than 0. Okay, so it's a reflected, or it's a time reversed version of xn. And the Z transform of this, it's easy to see, this is given as x tilde z equals summation n equals minus infinity to infinity x tilde n z raised to minus n, that is equal to n equals minus infinity to infinity x of minus n z raised to minus n, which is now set m equals minus n, implies this will be equal to limit infinity minus infinity becomes infinity, infinity becomes minus infinity. So, the sum still goes from minus infinity to infinity x of m z raised to minus of n, but minus of n is m z x of m z raised to minus m, which is m equals minus infinity to infinity x of m z inverse raised to minus m, and this is nothing but the Z transform of x evaluated at Z inverse or evaluated at 1 over Z. So, x tilde of Z, or basically if you look at the time reversed version of xn, that has the Z transform 1 over Z, and naturally the ROC will be 1 over Z element of R. So, for the ROC, for the Z transform, for it converge, we must have 1 over Z belongs, it converges, remember the Z transform x of Z converges where Z belongs to R. So, since this is x of 1 over Z, we must have for convergence 1 over Z belongs to R, which means the ROC must be equal to 1 over R, that is the inverse of any element, that is ROC R tilde equals basically all elements C T such that 1 over T belongs to R, that is the inverse of all the elements in R, inverse of all the elements in R. Okay, the Z transform, possibly with the exception of 0, because inverse of 0 does not exist. Okay, Alright, so that is the Z transform of the time reverse signal x of minus n, which is x of capital X, or the x of 1 over Z. Alright, let us look at another property. Let us see what happens when you multiply the signal by n. When you multiply the signal by n, now consider the signal xn, which is Z transform x of Z with ROC given by R, then x of Z will be summation n equal to minus infinity to infinity xn Z raised to minus n. Now, if you differentiate this dxz over dz, if you differentiate this, we have summation n equal to minus infinity to infinity minus n x of n z raised to minus 1 equals minus n equals minus infinity n x of n z raised to minus n. You can bring the z inverse outside, so this will be minus z inverse, which means minus z derivative of x of z equals n equals minus infinity to infinity summation n x n z raised to minus n, and this is, remember, you can look at this Z transform of n x n. So, the signal, that is time multiplication by n, that is the signal n x n has Z transform minus z dxz divided by, so multiplication in time is basically differentiation in the Z domain. So, this is multiplication differentiation of the Z transform. Let us look at one final property, that is the accumulation, which is similar to integration in time. So, we have the accumulation property where we have yn equals summation k equals minus infinity to infinity x of k, or k equals minus infinity to n x of k. So, this is termed as an accumulator, which is similar to an integrator for continuous time. Remember, we can have an integrator which is of the form integral minus infinity to t x of tau d tau. This is an accumulator, or basically an integrator for continuous time. Okay. And now the Z transform, so of this can be obtained as follows. Now, you can see that y of n minus y of n minus 1, if you consider y of n minus y of n minus 1, well, this is, you can simplify it as summation k equals minus infinity to n x of k minus summation k equals minus infinity to n minus 1 x of k which is basically, again you can see the only term that survives is x of n. Now taking the Z transform, now take the Z transform, and what you observe is that y of z minus Z transform of y of n minus 1 is Z inverse y of z. This is equal to x of z, which implies 1 minus Z inverse of y of z equals x of z, which implies y of z x of z divided by 1 minus Z inverse. Okay. So, or you can simply also write this as z x of z over z minus 1. So, you can see this adds a pole in addition to poles in x z, adds pole at z equals 1 in addition to the poles in x z. So, ROC has to be, so ROC, of course, since we have a pole at z equal to 1, if this is a right handed signal, you remember you are accumulating it, assuming this is a right handed signal. So, the ROC has to be magnitude of z greater than 1, correct, and previously the signal x of n has an ROC R. So, the ROC must be intersection of this, that is R and the region magnitude z greater than 1. So, the ROC, if the ROC of xn, let us say if xz has ROC equals R, since you are adding a pole at z equal to 1, the net ROC will be the previous ROC intersection magnitude z greater than 1. For instance, if the previous ROC for instance does not include a part of the region, for instance does not include, for instance let us say the previous ROC, let us take a simple scenario, let us say we have the previous ROC which already includes, for instance let us say this is the previous ROC corresponding to this, let us say this is a pole and this is z equals 1, and let us say this is the unit circle and this is let us say z equal to 1. So, the previous ROC already includes the region magnitude z greater. So, this is magnitude z greater than, has to be greater than 1, and the previous ROC, let me just write it slightly. This is the unit circle, and so this is your pool z equals 1, and this is let us say this is the unit circle, this is the pole, and let us say this is the ROC, previous ROC. Now, the previous ROC already is the region in which magnitude z is greater than 1. So, the previous ROC is modified, otherwise it has to be modified appropriately. So, the ROC will be the previous ROC or intersection with the region magnitude z greater than 1, alright. So, we will stop here and look at other aspects in the subsequent modules. Thank you very much.